Hello everyone, welcome back to the course on Electrical and Electronics Engineering. In today's session, we are going to see the fundamentals of single-phase AC circuits and analysis of pure resistive, inductive and capacitive circuits and the combination of them. So coming to the AC circuit, we need to know different types of power and power factor. Actually, there will be a real power, reactive power, apparent power. So what do you mean by real power? Real power in the sense it's a true power, or we can call it as average power or simply power, which is denoted by capital P is equal to the formula for power is voltage into current, that is multiplied by cos phi, or we can write as Vrms Irms cos psi, or in terms of magnitude means magnitude of V, magnitude of I cos psi, or in terms of only current and resistance means magnitude of I square R. The unit of real power is watts, where phi is the angle between the voltage and current. Coming to the reactive power, which is represented by Q, it is equal to the product of voltage and current and sine of the angle between the voltage and current. So in terms of Vrms into Irms, it is Vrms Irms into sine psi. Its unit is different. It's not watts, it's a VAR, that means volt ampere reactive. That's the unit of reactive power. The same comes here, reactive. What is apparent power? Apparent power is denoted by S, which is also a product of voltage and current. But this apparent power can be expressed in terms of real power and reactive power, that is equal to square root of real power square plus reactive power square. Its unit is volt ampere. What is power factor? We have included this cos psi power factor in real power, right? That is nothing but the ratio of resistance to the magnitude of the impedance. So both is a common thing. Resistance and impedance have a common unit ohm, so it doesn't have any unit, right? Where psi is the angle between voltage and current, we already know, and the magnitude of impedance is root of R square plus XL minus XC the whole square, where XL is the inductive reactance, XC is the capacitive reactance. Now we are going to analyze the pure resistive circuit. So in this circuit there is only one resistor, okay, and voltage AC current AC supply is given and a current is flowing there. So the response to the electric circuit to the AC current can be studied, okay, by passing this alternating current through the elements, either resistor individually, inductor and capacitor. First let us see about pure resistive circuit. Now we are applying the sinusoidal voltage, the small v equal to Vm sin omega t. The resulting current has an instantaneous value, the I small I equal to Im sin omega t. By Ohm's law, we know that Im equal to Vm by R. It's a ratio of voltage and resistance. Regarding the phasor representation, in each of this analysis of individual thing, we will see the phasor representation and waveform and power factor. These are the three things we are going to concentrate. So in pure resistive circuit, there is no phase difference between the voltage and current. Both lies in the same reference. If voltage is taken as a reference phasor of voltage and current, the angle between them is going to be 0. Waveform, how it is represented? E is the voltage wave, I is the current wave, complete cycle, and power is the product. So it turns out to be only this positive peaks. Power factor, it's a cosine of the phase angle between the voltage and current. So cos, you see the voltage angle between voltage and current, there is in phase, right? So it is 0. So cos 0 is 1. So the power factor is unity in pure resistive circuit. Coming to the pure inductive circuit, we place one inductor and pass the alternating voltage, okay, and it has a self inductance of L henries. So here the self-induced EMF always opposes the applied voltage. So small v equal to L into di by dt. So if I want to find current, I have to find I have to take the, since it's a differentiation, I have to take the integral 1 by L integral v dt. So we know that this instantaneous value of current can be represented by Im sin omega t, but since the inductive reactance is written in the denominator, actually if it is a numerator it introduces 90-degree phase shift. Since it is in denominator, it will introduce minus 90-degree. So current is lagging the applied voltage by 90-degree. That only has represented as a phasor diagram. Okay, so for the waveform, we draw the voltage waveform starting from 0 degree, but current waveform, it start delayed by 90-degree phase angle. This is for pure inductive circuit. Now we will need to find the power factor. For that, we need to know psi is the angle between voltage and current, which is nothing but 90-degree. Okay, if you substitute this phi equal to 90, if you want to find the real power, it's a product of voltage, current and cos psi. So cos 90 is 0. So everything turns out to be 0. So real power is 0. So it doesn't consume any real power. A pure inductor doesn't consume any real power. Whereas for the power factor, since the angle is 90-degree, cos theta also, that is cos 90 also 0. The power factor for the pure inductive circuit is 0 lagging. Since the current is lagging, it is 0 lagging. Now let us see for pure capacitive circuit. In this circuit, we know the sinusoidal applied voltage. This expression we know. Now we find the equation of capacitor. The voltage is 1 by C integral I dt. So, since the capacitive reactance introduces minus 90-degree, it is in denominator. If it comes to numerator, we have to write plus 90-degree. So this is for current. Instantaneous current is Im sin omega t plus 90-degree. So the current leads the applied voltage by 90-degree. So the phasor diagram we have seen earlier. Now for the waveform, the current waveform has to lead. So this is the first waveform is a leading waveform, leading by 90-degree. It started 90, but the voltage started 0. Now let us see about RL series circuit. Here the alternating voltage is applied to a combination of resistor and inductor, where VR is the voltage across the resistor, VL is the voltage across the inductor. So the instantaneous voltage is Vm sin omega t, that's the applied voltage. Its current equation is going to be Im sin omega t minus I. Since inductor will introduce lagging current, right? So this is a phasor diagram. Voltage is a reference and current leads the voltage by psi, even though it's a RL series combination. So waveform also we have to draw voltage starting at voltage waveform starting at 0-degree, but current waveform lagging by psi angle or phi angle. Okay, impedance of the circuit is going to be the ratio of voltage and current, and that impedance can be written as resistance plus it's a positive reactance JXL. In terms of this is a rectangular form. In polar form, we have to represent as a magnitude of the impedance value and the angle between them. Okay, R is a resistant, XL is an inductive reactance, where this XL can be computed from 2 pi FL, which unit is ohms. This is a voltage diagram where we know that in purely resistive, voltage and current are in phase. So we are drawing along here. But it's a inductive circuit means current lags but voltage leads, right? So it leads this resistive voltage, and we are writing as IXL. And the final voltage is going to be I in current into impedance, IR, right? Current into impedance. So if we want to represent as an impedance diagram, we have to remove the current part and voltage part and write only the resistance, that impedance terms, resistance, reactance and impedance. The magnitude of V is going to be root of this. Since it is the hypotenuse, it's a square of VR square plus VL square. And the impedance also same, magnitude of impedance is root of R square plus XL square. The voltage across the resistor VR is magnitude of I into R. Across the inductor it is VL, that is magnitude of I into XL. Now let us see about RC series circuit. Here the resistance and capacitor, resistor and capacitor are connected in series along with the sinusoidal voltage applied. Its value is Vm sin omega t. Since there is a capacitive reactance, so the current is leading, right? So Im sin omega t plus phi. So we have to draw the waveforms in that manner. What is a voltage waveform? Current is leading, right? And current also in the phasor diagram we have to draw as leading the voltage by phi angle. Impedance is going to be R minus jXc, since capacitive reactance is negative, and the phasor angle also in the polar form, magnitude of impedance is at angle minus phi. R is a resistance, Xc is a capacitive reactance. This capacitive reactance is equal to 1 by 2 pi Fc, whereas XL is 2 pi Fl, but here 1 by 2 pi Fc. The voltage diagram and impedance diagram also get inverted, right? It turns out to be inverted because here capacitive reactants will introduce current lead, but they introduce a which is equivalent to voltage lag. That capacitive voltage lag will be there, and we have to draw in opposite quadrant. And similarly, the impedance diagram. So magnitude of V is nothing but root of VR square plus VC square. Impedance value is root of R square plus XC square. Voltage across the resistor is magnitude of I into R. Across the capacitor is magnitude of I into XC. This is about RC series. Now let us see about in the all the three combination. Resistor, inductor and capacitor, all three are placed in a series. Then we are applying the instantaneous voltage and the current is flowing. So depending on the value of the reactance, inductive reactance and capacitive reactance, this circuit will behave. Even though all the three elements are connected, it will behave as a RL circuit or RC. When XL is greater than XC, that means the inductive reactance dominant means it will behave as RL circuit. If this inductive reactant doesn't dominant means it will behave as RC circuit. The impedance is going to be the sum of all R plus JXL. This will introduce negative reactance, so minus JXC. Okay, J we can take common and XL minus XC we can write. XL XC formulas we just now saw earlier. The impedance unit is ohms. Here the J can be written as I also. Its value is root of minus 1. Here F is the supply frequency which is in hertz. So we have two cases to understand. XL greater than XC means we know from the previous analysis it behaves as RL circuit. So the voltage lead will happen here. Okay, and we have to draw x-axis resistance, this y-axis, since it is leading XL minus XC, and this is the overall impedance. If it XC is larger, actually voltage will lag, so we have to draw in an inverted way, resistance on the top and this lagging, then this is a final impedance. Now let us solve problems based on the analysis of RL, RC, RLC circuits. So here a resistor of 10 ohm, inductance of 50 millihenry and capacitance of 150 microfarad are connected in series. So RLC, R are connected and it is supplied by 200 volt 50 hertz supply. We are supposed to calculate the inductive reactance, which is nothing but XL, capacitive reactance XC, impedance that is EZ, current that is I, power factor, okay, and that is cos psi, then real power that is power P, normal power. And we are also supposed to find the voltage across R, L and C, VR, VL and VC. First let us find one by one. XL is nothing but 2 pi FL, frequency is given 50 hertz, inductance 50 millihenry is given, so we substitute and find the answer in ohms. Similarly XC by 1 by 2 pi FC also we substitute and get. To find the impedance, which is equal to resistance value 10 ohms plus J, XL just now we have found early, that value minus XC and ohms. Actually the final answer is going to be the negative reactance, or we can write in terms of magnitude also, root of R square plus XL square, like that, XL minus XC the whole square. For to find the current, we know it's a ratio of voltage to the impedance. Impedance just now we have found early. Using this complex quantity itself we can write, and we have to use our calculator in complex mode and find this answer. The unit is ampere. We can represent this rectangular form A plus J B format to magnitude angle format also. Power factor is cos psi. What is the angle that we have found earlier? The angle between the voltage and current, it is 28.8 degrees, so that we can substitute and find. How we are writing as leading power factor, because of this how to say this, XC, inductive capacitive reactance is more, right? So it's a leading power factor. And power factor can be found in other way, because we know that power factor can be written as a ratio of resistance to the impedance. I think we have seen earlier. Just I will show you once. Ratio of resistance to the impedance. We can write in that manner also. I think we have seen in the starting slide. Yes, ratio of resistance to the impedance, magnitude of impedance, or cos psi, both are same. So we apply and find, both are, we are getting the same answer. Okay, to find the real power, VI cos psi. We can use this cos this psi angle and find it in watts. Similarly, I square R also we can find from the current value that we have computed earlier. So power value approximately ranges from 3000 to 3100 watts. To find the voltage across the resistor VR, it is magnitude of I into R. Okay, magnitude of I is 17.5. Only magnitude we are taking into the resistance. Similarly, VL is magnitude of I into XL. XL is given, we have computed as 15.7 here. Okay, similarly, VC is magnitude of I into XC. That also we have found previously. Okay, I is 17.5, XC is 20. Here a inductive coil is given, which is taking a 10 ampere current and dissipating 1000 watts when connected to a supply of 250 volt and 25 hertz. We are supposed to find the impedance, resistance, reactance, and the power factor. So what is given in this question? Inductive coil, okay, is present along with the resistance. So RL circuit is given with the supply. Okay, but R value is not given and L value also not given. So to find the impedance, we need to know what is the resistance and the reactance. So from the given data, we know from power formula is I square into R. From that, since current is known, from that we are finding the R value, that is P by I square. We are finding 1000 watts by 10 ampere square is 10 ohms. So to find the impedance, to find the magnitude, it is going to be what? Voltage to 50 volt divided by 10 ampere, that is 25 ohm. To find the is a magnitude of impedance. To find the original impedance, we need to know the reactance also. That is equal to root of R square plus XL square. Okay, but we need reactance, so it is going to be root of Z square minus R square. Magnitude of Z square is 25 square minus 10, 22.912 ohms. So impedance we can write R plus JXL, or we can write in polar form 25 angle. We have to find that, okay, and write it in ohms. So the resistance is 10 ohm, reactance is 22.91. For the power factor, we know that it's a ratio of resistance to the impedance. Resistance is 10 and the magnitude of impedance 25. It's a 0.4. Since it's a RL circuit, it's a lagging power factor. Hope you understood this analysis of single phase AC circuits, right? Thank you everyone.